Chapter 3, Section 1, Substances are made of atoms. In this section, we're going to begin our exploration of atomic theory. So we know from the previous section that a theory is something that has been proven by hypotheses, but then someone has come along with a new discovery and has changed our ideas. Okay. So this is really a history lesson. Okay. So this begins our look at the atom. So in other words, we're talking about the atomic theory. And the atomic theory is based upon the idea that atoms are the building blocks of all matter. So the foundation of chemical atomic theory comes from three laws that we're going to look at to start with. The law of conservation of mass, which was given to us by Lavoisier. The law of definite proportions, and the law of multiple proportions. So we're going to begin our discussion with the law of definite proportions that says that a chemical compound contains the same elements in exactly the same proportions by mass, regardless of the size of the sample or the source of the compound. So the compound we're going to look at in the animation is sodium chloride. We're going to see that sodium chloride comes from a salt mine and eventually winds up in your salt shaker at home. And we're going to see that no matter if we're looking at the salt directly from the salt mine or the salt that comes from your salt shaker, the amount of sodium and the amount of chlorine in each of those samples are exactly the same.
Table salt, sodium chloride, always consists of 39.34% by mass sodium and 60.66% by mass chlorine, no matter how big the sample is or where it comes from. The salt in the walls of a salt mine might consist of 786.8 tons of sodium and 1,213.2 tons of chlorine, but the proportion is still 39.34% by mass sodium and 60.66% by mass chlorine. A salt shaker with 100 grams of salt would contain 39.34 grams of sodium and 60.66 grams of chlorine. The proportions are still the same. A single grain of salt still contains 39.34% by mass sodium and 60.66% by mass chlorine.
The next foundation of a chemical atomic theory is the law of conservation of mass. The law of conservation of mass was mentioned in the previous video notes because we mentioned that a law is a statement or mathematical expression that reliably describes the behavior of the natural world. Okay. So the law of conservation of mass states that mass is neither created or destroyed during ordinary chemical reactions or physical changes. Okay. Now, the reason why this mentions ordinary chemical reactions is because we can have nuclear reactions, okay, that convert mass into energy. So there's a loss of mass there. Okay. So in our terms, we're looking at chemical reactions that would occur in the chemistry classroom. Okay. And again, specifically, let's reference the lab with sodium bicarbonate, which is baking soda, and vinegar. Okay. So when you do this lab, you mix it in a bottle that has a closed container because we don't want the gas to escape. We measure the mass before and we measure the mass after, and it should be exactly the same. Because in a chemical reaction, what's happening is the atoms are rearranging themselves. And we're going to see the law of conservation of mass evident in the first atomic theory we're going to mention in this video note, which is Dalton's atomic theory. So let's look at an animation.
This law of conservation of mass states that the total amount of matter in a closed system remains constant. In other words, matter cannot be created or destroyed during ordinary chemical reactions. In chemical reactions, such as the combustion of this match inside a closed container, we find that the mass of the starting materials is the same as the mass of the ending materials. The law of conservation of mass explains why we represent chemical reactions as balanced chemical equations. The number of each atom on each side of the equation is conserved, representing that mass is conserved. The law of conservation of mass works for most things you encounter in daily life. In 1905, however, Albert Einstein showed that matter and energy could be equated with his famous E=mc² equation. The implication of this is that the law of conservation of mass will not hold for cases where large amounts of matter were converted to energy, such as in nuclear reactions. The law was revised to become the law of conservation of total mass and energy.
So let's look at some images. So in this image, we have phosphorus pentachloride, and the green circles are representing chlorine, and the gold one is representing phosphorus. This decomposes into a phosphorus trichloride molecule and a chlorine molecule. Again, if you look, the number of gold circles on both the reactant and product side are equal. And if we look at the number of green circles, which are representing chlorine, we would see that there are 5 chlorines on both the reactant and product side. Okay. So this is a different reaction. We're combining sulfur and oxygen to make sulfur dioxide, but it still obeys the law of conservation of mass. We can clearly see that there is 1 sulfur atom on the reactant side, 1 sulfur atom on the product side. There are 2 oxygen atoms on the reactant side, and there are 2 oxygen atoms on the product side. Okay. The last law we're going to look at, which is the foundation of chemical atomic theory, is the law of multiple proportions. So the law of multiple proportions says that I have 2 or more different compounds. However, they're made up of the same 2 elements. For example, carbon monoxide, so CO, and carbon dioxide, which is CO2, would be an example of the law of multiple proportions. Okay. It continues to state that the ratio of the masses of the second element combined with a certain mass of the first element can always be a ratio of small whole numbers. Right. So let's look at an example of the law of multiple proportions. This example is going to use hydrogen and oxygen.
The law of multiple proportions states that the mass ratio for one of the elements in a compound that combines with the fixed mass of another element can be expressed in small whole numbers. This law can be demonstrated using 2 compounds formed from hydrogen and oxygen, water and hydrogen peroxide. A 9-gram sample of water results from the reaction of 1 gram of hydrogen gas with 8 grams of oxygen gas. A 17-gram sample of hydrogen peroxide results from the reaction of 1 gram of hydrogen gas with 16 grams of oxygen gas. We note that the amount of hydrogen in both samples is the same. The ratio of the masses of oxygen in these 2 compounds is 8 to 16, or 1 to 2. From this, we can deduce that there must be twice as much oxygen in hydrogen peroxide as there is in water, and the same relative amount of hydrogen in both. It does not tell us, however, exactly how many atoms of each element make up the molecule. We now know, for example, that both water and hydrogen contain 2 atoms of hydrogen per molecule, a fact we could not deduce from the law of multiple proportions, which simply told us that we have the same relative amount of hydrogen.
Another example of a law of multiple proportions are compounds with nitrogen and oxygen. So this image shows us nitrogen monoxide and nitrogen dioxide. And again, if we look all the way to the right, we can see that if I have the same relative amounts of nitrogen, which is 1 gram, the ratio of the oxygen in nitrogen monoxide to the amount of oxygen in nitrogen dioxide would be a 1 to 2 ratio. It does not necessarily mean that the subscripts are 1 to 2. So let's look at our first atomic theory. Okay. Dalton's atomic theory has 5 parts. you are responsible for knowing all 5 parts of Dalton's atomic theory. There are 2 of them that are no longer true, so I will mention them in this video. Number 1, he says that all matter is composed of extremely small particles called atoms. He also says that atoms cannot be subdivided, created, or destroyed. What this really means for us is that he believed there is nothing smaller than the atom. So his picture of the atom was that the atom was a solid ball. Well, it's true that all matter is composed of atoms. However, through experiments by Thomson and Rutherford and another scientist by the name of Bohr, we have revised this part of the theory, and we know that there are smaller parts than the atom. There are electrons and protons, and that'll be part of our next lecture. Number 2, he says atoms of a given element are identical in their physical and chemical properties. So what this means is that, for example, all atoms of carbon are exactly alike. Okay. Probably most of you have heard of carbon-12 and carbon-13. Okay. They're named differently because there's something different about them. What's different is their mass. They have a different number of a particle called a neutron. So these atoms are isotopes of each other. So once the discovery of isotopes came along, we disproved this part of Dalton's atomic theory. Number 3, atoms of different elements differ in their physical and chemical properties. So what this means is that if I were to have atoms of sodium and atoms of chlorine, they would have different physical and chemical properties. For example, sodium makes up a silver-colored solid. Chlorine is yellowish green gas. So they have different physical properties. Okay. In terms of chemical properties, they are both very reactive, but in different ways. One of them gives up electrons in order to react. The other one gains electrons in order to react. Number 4, atoms of different elements combine in simple whole number ratios to form chemical compounds. And finally, number 5, in chemical reactions, atoms are combined, separated, or rearranged, but never created, destroyed, or changed. So this should really sound really familiar. So this part of Dalton's atomic theory came out of Lavoisier's experiments in regards to law of conservation of mass.